Hello everyone. So activity 5.5 is just an extension of 5.4. We're again looking at solving rational equations. So in this one we will be able to solve them algebraically and also graphically. And also if we have an equation that has multiple variables in it, we'll know how to solve for a specific variable. So we start off talking about an auditorium that has different exit doors. It has 3 different exits. Each one can empty the auditorium on its own at a different rate. So the first exit can do it on its own in 10 minutes. The second exit used by itself would take 8 minutes to clear the room, and the third exit can do it by itself in 5 minutes. So our main goal here is really to figure out how long will it take if all 3 exits are used. Okay, so now we're starting. The first question is, if only the first door is open, what fraction of the auditorium can be emptied in 5 minutes, 2 minutes, and then 1 minute? Okay, so we're really just focusing right now on the first exit that takes 10 minutes to do the whole thing. So we're trying to figure out, like, how fast is it working per minute. So if it takes 10 minutes to clear the whole auditorium, in 5 minutes, so for 5 minutes, it can clear half of the auditorium. Okay, it can get half of the job done because it's got half the time. In 2 minutes, if it takes 10 minutes to do the whole thing, well, 2 minutes, then it can do 1/5 of the auditorium. It can clear 1/5 of it. And then in 1 minute, if I only have 1 minute out of 10, well, then it can do 1/10 of the job. It can clear 1/10 of the auditorium. So now these are really rates. This is really saying how much of the job it can do per minute. Okay, so the rate at which the door can be used to empty the auditorium is a fraction of the job that can be completed in 1 minute. So in this case, the units are auditorium per minute. Okay, so we're going to determine the rate for each one of those exits. So the first exit takes 10 minutes to complete. So what fraction can it do per minute? So that its rate would be 1/10 per minute. The second one takes by itself 8 minutes, so it can do 1/8 per minute of the job. This could be extended for any kind of problem where things are working together. Most algebra books you see 2 pumps working together, 2 people working together to paint a house, things like that, okay, where people are working at different rates. So this can be extended for a lot of things. And then that third exit takes 5 minutes, so it can do 1/5 of the job, 1/5 of emptying that auditorium per minute. So they're actually giving us a formula to model here, and we'll use this one over and over. So it's showing us down here that if you look at if 3 things are working together, each at their own rate, this is how you would find the total time it takes to do it. Time it takes if they're all working together. Whereas all these right here are all the individual times. So if we take that formula, okay, and we write the equation that can be used for the auditorium to be exited using all 3 exits, I'm going to write that in terms of our problem right here. So the first one takes 10 minutes. The second one is 1/8 because it takes 8 minutes to do it, and then 1/5. Okay, and then 1 over t. T is what we're looking for here. This is the one we're trying to find. How long does it take if they all 3 work together? So solve this equation graphically. So if you want to go on your calculator and figure out and put all of this right here in y1 and put this in y2 and figure out where they intersect, you'll find that they intersect at about, t is going to be approximately 2.353, and that would be minutes. That's how long it takes for them to if they're all working together. But I want to focus more on the algebraic way of solving these. Okay, so that's what we're going to do in this next slide. All right, so now we're taking a step back from the problem that we just had, and we're talking about a different one. So let me just step you through a little bit of this. For each of these examples, A and B, they're just using the LCD. So they're just having you find the LCD, the lowest common denominator, for 12 and 45. Everybody does these differently. They're showing you how to do it with the prime factorization. If there's another way that you like to find the lowest common denominator, then do that. The idea is when we get to an equation, we use that lowest common denominator to wipe out, to eliminate all the fractions. Okay, so you're just going through and look at these and make sure, like when I'm doing the LCD of this one right here, I'm looking at what is the lowest common denominator for 6 and 9, and that would be 8. The lowest common denominator for x and x squared, I take the highest power of these. So y to the third and y would be y to the third. So that's how I'm getting my lowest common denominator there. So let me show you how we're going to use this. Okay, so let's go back up to this was the problem we were just looking at right here with the exits working together. So determine the lowest common denominator. So if I look at the lowest common denominator, first I'm looking at the 10, 8, and 5. So that's a 40. And because one of those denominators has a t in it, I also need a 40t. And you'll see how I'm going to use this and why I needed all that. So what I'm going to do to make this whole thing easier to solve is I'm going to take this whole equation and I'm going to multiply the whole thing by 40t. Okay, and watch what happens. When I do that, I'm distributing that 40t to everything. I get 40t over 10 plus 40t over 8 plus 40t over 5 equals 40t over t. Okay, so maybe it doesn't look like it helped me very much yet, but watch this. So the whole reason I did this is because if 40t should cancel with every denominator. So watch this. This will cancel to a 4. Right? This will cancel to a 5. This will cancel to an 8. And this will cancel to, that's t, and t is canceling to a 1. So my new equation now is 4t plus 5t plus 8t equals 40. Much, much easier to solve. Okay, I eliminated all my fractions. So I used the 40t because it would cancel with each one of those denominators. So let me just come over here for a second. So now I have 17t equals, I have a nice linear equation to solve. So I end up getting it's equal to 40 over 17, which is approximately 2.353 when you round it. Okay, how does it compare to the one we got graphically? It's the same thing. Okay, obviously it doesn't matter which way I do it. But I did it algebraically by finding that lowest common denominator and multiplying it through the whole equation, and that will eliminate all my fractions. Okay, so let's see what we've got. An auditorium is equipped with 2 ventilation fans. The first can exchange the air in 4 hours. The building code requires a complete exchange of air in the room every 3 hours. Okay, to model the situation, we're going to use the same equation. Okay, the reason why it looks a little different than the last one is because we only have 2 ventilation fans working, so we just only have those T sub 1, T sub 2. Okay, so what we're trying to figure out here, they're saying that this right here, they're saying the building code requires that it has to be exchanged every 3 hours. So they're saying that that total time has to be 3 hours. So we just have different information here. So we know that the first fan can do it in 4 hours alone. We know that the total time for it to be ventilated has to be 3, and then we don't know this. So it looks similar to the last one we had, except the other one had our unknown on the right hand side of the equation. This has ours on the left. So we're going to go through both ways again to solve this. So our first way would be to take this and put it in y1 and this in y2, doing it graphically. So I did that ahead of time. So I've got my 2 graphs. If you do those on the calculator, that's what you'll get. Keep in mind y equals 1/3 is just a horizontal line at 1/3. And you'll find that when you solve this, you end up this intersection point right here, around there, is about 12. Okay, so now we're going to do it algebraically. So now if I come over here Let's pick out the LCD. Okay, the LCD would be 12x. So I'm going to multiply the whole thing by 12x on both sides, and let's see what I get. I get 12x over 4 plus 12x over x equals 12x over 3. So let's do our crossing here. This cancels to a 3. Those drop to a 1 right there, and this drops to a 4. So what's my new equation? My new equation now is 3x plus 12 equals 4x. And I get x equals 12. Okay, so that other fan can do it in, the second fan can do the job in 12 hours, and then total the fans would do it in 3 hours. Okay, so this other one right here, it's the same kind of thing, except one fan can work twice as fast as the other. Okay, so we're using the same formula right here. Okay, so one fan can do it. I'm just working together, the two fans can exchange the room in 4 hours. Okay, so we know that that is our other side of the equal sign from here. That's when they're working together. We don't know the times for the single fans, but we do know that one of them can do it in half the time as the other. So one time will be twice of the other. So again, algebraically, if I'm trying to solve this, my LCD would be 4x. So I'm going to multiply through by this 4x, and let's see what we get. We get 4x over x plus 4x over 2x equals 4x over 4. And when I do my canceling here, these drop out to 1. Okay, so I end up getting 4. And then that drops with that to 2. The x's also drop, plus 2. And those drop out, and I get x over there. So x is 6. Okay, so the first fan can do it in 6 hours, and then the other fan could do it in 12, twice as much. And you can check that one doing it graphically. Okay, so I'm going to let you go through this one. Now the next part they're doing for example 2 is having you, they're showing you, stepping you through solving it for a specific variable, still using the LCD, and then getting a variable alone. I want you to keep in mind when you're doing your homework, if they want you to use, these are the two formulas you're going to use all the time. This one right there, and then this one right here. So since we have both of them right here, you don't have to do all of this work every time. One is solved for one, they're just in different forms. So if you want it to be solved for that capital T, well then you just come back and use this one each time. I want to step you through, there's one on the next page that doesn't have the work for it, so I want to make sure I give you the work for that. Just taking a new formula, since you can follow that other one on the activity. So this one, it's the same looking kind of formula. They want us to take this formula and solve it for f. They want us to get f alone. So my first thing to get f alone is to get it out of the denominator. So the LCD for all of this is PQF. So if I take the whole thing and I multiply the whole thing by PQF, let's see what I get. I get PQF over P plus PQF over Q equals PQF over F. Okay, so let's do some crossing. That was my whole point. The P's drop out of that, the Q's drop out of that, and the F's drop out of that. So I get QF plus PF equals PQ. And if I want these F's by itself, since there's two of them, I've got to factor an F out and say Q plus P. I'm undistributing there. If there's two of them and I need to get it alone, I've got to pull it out. So I can now get it alone by dividing by Q plus P. Okay, so that drops there. So P, whoops, not P. Let me make that into an F. F equals PQ over this Q plus P. So these formulas do the same thing, they're just solved for different variables. It's just like having an area formula. The one time it's solved for area, one time maybe it's solved for length or width. We can use them in either form, but sometimes if I am plugging in to find f, well maybe this one that I'm highlighting right there, maybe that one's easier to work with. Okay, so use some of these practice problems in here on page 528 to practice solving for different variables. Those exercises, those answers are always in the back of your book.